Good evening and welcome to your AP Stats Notes Online. Again tonight, we've got just a couple more slides to cover and take a look at an example. And then we'll be done with this section and actually be ready to, we'll have one more night of notes from section 4.3 and then we'll be ready to start working towards a test. By the way, quick quiz probably coming on Friday. If not Friday, then maybe another Monday quiz, but I'd rather try to get to it on Friday. We'll see. We'll talk again in class tomorrow and see what happens. Okay? Okay. So we've been talking about how to properly set up your experiments. We've got the three principles we have to keep in mind. Random, control, and replication. If you don't know what those mean, you need to. And you need to go back and take a look at those three principles again and then be able to talk about those three principles in a particular experimental setup. And we talked about what the placebo effect is, and we talked about what statistically significance was yet again. Again, we talked about it a lot in the Coke versus Pepsi activity. And then again, we are taking a look at the distracted driver example now. So one of the things that we have to really, again, make sure that we take care of is controlling for these lurking variables. You know, comparison groups, randomly assigning our subjects, trying to get those lurking variables out of our response, out of our experiment, so they can't drive our results and only our explanatory variable can. A randomized, completely randomized design is the simplest way to try to do that. But we saw this with sampling too. Just a simple random sample was the easiest way to go get a random sample. But sometimes we have to do some things to make sure that we get a good mix between groups. Because maybe there's a characteristic that our population has that will cause them to react differently, whether it's answering a question differently in a survey or react differently to a treatment in an experiment. And so a completely randomized design is not always the best method. What we can do then is if we know that that's going to happen from our population and we can't design it out, design that characteristic out in our completely randomized design, then what we have to do is create what we call blocks. Okay? Now blocks are a lot like strata in samples. I'm going to say that, but you need to be very careful when you talk about these. Blocks are like strata, but you can't talk about stratifying in an experiment, okay? I'm just saying this so that you understand what we mean by blocking, okay? But a block is a group of experimental units that are known before you even start your experiment to be similar in some way that will cause them to affect the response to the treatments, okay? The most common way to block is to block by gender. Men and women, we react so many different, we react differently to so many different things that very often we want to separate men and women and then run the experiment on those guys and see how the treatments affect those guys separately. So when we do that, we've created an experimental design called a randomized block design. And so we'll create blocks and then we'll randomly assign within the blocks to our treatments, 2, 3, 4, 7, however many there are, and then compare the results once we're done with our experiment that way, with our blocks. Okay? So moving forward here. And so a couple of things keep in mind. Blocking is another form of control. Now again, we're trying to adjust for a lurking variable that we don't want to affect our results as much as our treatment, as much as our explanatory variable. So it's definitely a form of control. And also, if you're going to block in an experiment, if you're going to separate out your subjects into two groups before you randomly assign, you have to be able to explain why. Okay, I'll back up for a second. Right? So we form blocks based on the most important, unavoidable sources of variability among the experimental units. Right? Randomization will average out the effects of the remaining lurking variables and allow an unbiased comparison. So we're going to randomize after we've blocked. So the idea is you control what you can. All right? I know these lurking variables are here. I have a way that I can design my experiment and randomly assign, and I can confidently take care of those differences. And if there's something that you know you're just not going to be able to design out, then you create blocks. So you block what you can't control, and then you randomize to create those comparable groups. Okay? When you block, okay, you need to be able to explain why. Okay? We got to be able to explain why. And again, usually the blocking variable has some sort of association to the response variable that we can't get rid of. So talk about that. You know, going back to the diet versus exercise sort of example I threw out there off the top of my head. You know, I want to know if a well-balanced diet or alone or exercise alone will help you lose weight. Well, men and women store fat differently. And so I don't want to run the risk of randomly assigning all women to diet and all men to exercise and then try to compare those two groups. They're going to react differently. So what I'll do is I'll block. I'll say, okay, I'm going to put my women over here, my men over here, and then I'll randomize the women to the two treatments, diet and exercise, and randomize the men to the two treatments, diet and exercise, and see what happens from there. Okay? Again, gender is the most common, but definitely not the only way. Okay? We can also do this when talking about chocolate chip cookies. Okay? Yummy. Anne is an avid baker who would like to compare two different chocolate chip cookie recipes, A and B. Okay? So that's her explanatory variable, the recipes. So she recruits 10 volunteer taste testers. Yay, pick me, pick me, pick me. Anyway, to rate each type of cookie on a scale from 1 to 5. She'll make 10 of each type of cookie for a total of 20. Each cookie tray will only hold 10 cookies, so she'll use 2 trays and bake them at the same time in the same oven. Good. Same time, same oven, so there's no atmospheric pressure differences and heating differences and things like that. But room is an issue. She'll put 1 sheet on the lower rack and 1 sheet on the upper rack. Now, anybody who's ever done any baking knows that the lower rack and the upper rack bake differently. One's closer to the coils, providing the heat. So let's go through and talk about the design here then. Okay? All right, so what do we know? We know that we need to bake the cookies at the same time in the same oven, right? So that the baking is the same. And that controls for a lot of the lurking variables that might be there. Okay? So to design this, go back. Okay, go back. Okay? Here's how we want to show. And again, I'm going to do it in a diagram. And then I think that's a lot easier. So here's what I know. I've got 20 locations that I am going to choose. Okay? Excuse me. 20 locations, or the 20 places I'm going to put the cookie, are, I guess, my experimental units. It's kind of weird to think of it that way. okay, but 20 cookies. And I know there's going to be a baking difference from the top to the bottom rack, so I don't want to run the risk of randomly assigning, happen to get all of recipe A on the top rack and all of recipe B on the bottom rack, and therefore run the risk of the difference in the taste of the cookies being the difference in the baking in the oven. So what I'm going to do is block them, right? So I'm going to create a block that consists of 10 top rack locations being block 1, and 10 bottom rack being block 2. Okay. Then I'm going to randomly assign. Okay, we don't randomize until once the blocks are created. Okay, and so I'm going to randomly assign 5 cookies, 5 recipe A's, and then 5 recipe B's into those locations. Kind of weird to think about the locations. So 5 recipe A's to certain locations, and then randomly choose 5 recipe B's to be in locations on that rack, and then do the same thing down here. Randomly assign 5 recipe A's on this sheet and 5 recipe B's on this sheet. Okay? Now when we do that, once we apply the treatment, so we've got the recipes in here, now we're going to find our taste testers, and let's not even get started on how taste buds are different and whatnot. That becomes a little bit more complicated issue, but once we have our cookies, then we want to compare taste, 1 to 5, we want to compare taste with these guys, and then compare taste with these guys. Okay, we don't want to bring them back together because that sort of negates the whole reason for blocking to begin with. So, so that's what a randomized block design would look like. We got to talk about again our experimental units, how many and what are they, and then block them, and then be able to talk about why you're blocking right here. Top rack, bottom rack. That tells us what the blocks are. It might be worth adding a description in the bottom real quick that says something about, I know the top rack and the bottom rack are going to bake differently. And then we randomly assign, we'd have to describe down here in the paragraph form how we're going to do that, either using table D or the hat method or technology. And then we randomly assign our recipes to our 5 locations here. And then we want to compare taste. So you want to make sure that you add in what that response variable is into your design. And then, of course, what would have to follow would be a short paragraph on, again, explaining the blocks and then explaining how you're going to randomly assign. But that's a randomized block design. That's the idea behind it. It's kind of like strata, right? Where we break our population up into groups because we think that they're going to answer the same way, and then choose a few from this group, a few from this group, and a few from this group, so we get a good healthy mix. It's kind of the same thing, but blocks are for experiments and strata are for surveys, and you got to make sure you keep those separated. Okay? Now, a special type of block design, okay, is what's called a matched pairs design. And so the idea is to create blocks by matching pairs of similar experimental units. Okay? So we'll talk about that a little bit. A matched pairs design is a randomized block experiment in which each block consists of a matching pair of similar experimental units. Okay? So if I've got, in the form of, I don't know, what would be a good example of applying one treatment to, or two treatments, a treatment to 2 experimental units that are the same. When we might do that, I'll come up with a good example in a minute. But we have two options here. We can do that, and then chance is used to determine which unit in each pair gets each treatment, right? Say I want to test tires, right? I'm going to test tires, and so I'm going to take two tires. I'm going to see, all right, I've got two new tires here. I want to see which one performs the best, right? I don't know. And so what I'll do is, you know what, scrap it. I'll come back to it. That's hard. When you have two experimental units that you want to give the same experimental units and give them two treatments, it's not a good example. But anyway, moving forward, that's the idea, right? I've got two treatments, and I want to take two experimental units that are the same, they are identical, and apply the two treatments to those and just do them in pairs. Okay? Finding two experimental units that are the exact same can be tough, especially if you're talking about human subjects. And so sometimes a pair in a matched pairs design consists of a single unit that receives both treatments. Now that one's a little bit easier to come up with, right? That happens all the time with human subjects. Because you can't find two humans that are the same, that are exactly the same. It's very difficult to, depending on what you want to measure. So what we'll do is we'll take a single subject and apply both treatments to them and see what the difference is, amongst the two treatments in that same subject. So since the order of the treatments can influence the response, we have to use chance to figure out which treatment is going to be applied first for each unit. Okay. And we'll do something in class tomorrow, exploring pulse rate, whether you're sitting or standing. Do that as quickly as we can. But so the matched pairs can be where we take two experimental units that are the same and randomly assign the two different treatments to them, or it could be where we take one experimental unit and apply both treatments but randomly assign which one goes first. Okay? It's sort of the same thing as blocking. It's a lot like blocking, only we're creating blocks with pairs of our experimental units as opposed to bigger groups. Okay? We'll take a look at an activity tomorrow that will help maybe explain matched pairs a little bit more in a little bit better way for you. So, but that's it. That's what the two methods that we want to add on to as far as creating an experiment. We're going to do blocks if we think that we can't design out a particular lurking variable, and so we'll just separate based on that lurking variable and then randomly assign. Or we can do this guy, this matched pairs guy, which takes two experimental units that are the same and applies the treatments to just two of them to see what happens. Okay? And so that's it for this section. That's it. So some of the things you got to be able to do. Tell the difference between observational studies and experiments, right? Experiments have to have treatments. Some of the vocabulary, subjects, experimental units, explanatory and response variables, factors, those kind of things you need to be able to use appropriately. Understand the three principles of experimental design: control, random assignment, and replication. Talk about double blinding, right? When we need to double blind to help control for the placebo effect. So we've got placebo effect. The placebo is a fake treatment that we want to give to make sure that we're treating everyone the same. And then understand the idea of a block design and a matched pairs design, and be able to talk about when we want to employ one of those two methods. Okay? And then we've got one more section in this chapter. We're going to talk a little bit about the scope of inference, when we can make conclusions about the population versus cause and effect. Talk about the challenges of establishing causation, right? This thing causes this thing, and talk a little bit about the ethics in performing an experiment. Okay, that's it for tonight. Homework is assigned. I know you didn't have a lot of class time to work on the 4 problems from the night before. Hopefully you found some time to get those done. If you didn't, you can work on them now, or you can work on them in class tomorrow after our very fast, I promise, very fast matched pairs experiment. Okay? Enjoy your night. See you tomorrow.